So we have a couple of variations in here as well. STP is used to provide a loop-free layer 2 topology within a VLAN, or if it's per VLAN, or globally on the switch if you don't run per VLAN spanning tree. But with Cisco, you have to run per VLAN spanning tree. So if the attacker, for example, connects an unauthorized switch to the network, this can result in confidentiality loss due to switching functionality. Because we know that when a switch receives a frame for which the destination MAC address, if it's unicast, is not known to himself, he has not learned the MAC address, then it's going to flood that frame, which is, the feature is called unknown unicast flooding. It's going to flood the frame out on all ports in the VLAN that the frame was received on, of course, except the port the frame was received on. So again, if the switch receives a frame for which the destination MAC address is not found in the MAC address table, then it's going to flood that frame out on all ports, except of course the port it was received on, out on all ports in the VLAN where the packet was received on. So this also can affect root bridge selection, because if the attacker connects a switch which has a better root bridge priority, then that switch of the attacker can become the root bridge in the VLAN or in the network, which means because in the layer 2 path the traffic packet is being governed by the root bridge. So I'm going to have some block ports and some forwarding ports. Then it can happen that I'm going to end up sending the traffic via the attacker switch, and that could also is going to create again confidentiality issues, because the attacker is going to receive on its switch all of the frames, and likewise it's going to also optionally, or in some cases, going to create a bottleneck if the performance of the switch of the attacker, which became the new root bridge, is not as good as the performance of my original root bridge in the network, which had better throughput per second than the attacker switch. So STP attack mitigation, we have a couple of features. One of them which is called port fast. Port fast is not per se a security feature, but is required for other security features to defend against STP attacks. So port fast, to keep it simple, it does a lot of other things as well, but most importantly, whenever a port fast enable link is going to come up via somebody connecting something on a port or a channel shut on a port, then it's going to the feature is going to put the port directly to STP forwarding, bypassing the listening and learning state. So the port is going to be able to switch traffic back and forth instantly, as opposed to waiting 30 seconds for the port to go through all of the states like listening, learning, and then to forwarding. Port fast can be globally enabled or per port. It doesn't matter where you enable it, it's going to be the same behavior. But of course, because port fast puts the ports directly into STP forwarding state and it could create the loop, then if a BPDU is received inbound on the port, then the port fast state is being lost, and the switch is going to start negotiating the port role as regular, going through all of the states, blocking, listening, learning, and then forwarding or blocking. Now, to defend against the attacker, so the problem was that the attacker was putting a switch in the network, and that could create either a bottleneck or could create confidentiality issues. So either way, one good tool which I have to configure to defend against that attack is going to be the BPDU guard. So once I'm going to enable the BPDU guard feature on a layer 2 port, then as soon as on that layer 2 port I'm going to receive an inbound BPDU, which is going to happen if the attacker connects a switch, then the feature is going to put the port into what is called error disabled instantly. Error disabled, we've seen that the same functionality in port security is like a logical shutdown of the port, which likewise like in the port security case, the port recovery from the logical shutdown can be done either manually via channel shut on the port, or you can configure the switch to automatically try and recover the port each X seconds via the error disable recovery feature configuration, which is of course disabled by default. So let's see that happening. So what I have switch 1 and switch 2 connected. Let's see one use case. So what we're going to do is we're going to configure this feature is on your access switches. So like for example, if your network is like this, you have your access switches in here, 1, 2, 3, access 1, access 2, and access 3, where you have your users, your endpoints connected. So on the access port you have users, printers, phones, whatever on the access switches. And of course you're going to have then a distribution level or a core or a collapsed distribution core level, whatever it is, with maybe redundancy at the switch level. So this is going to be like distribution 1, distribution 2. You're going to go ahead and configure, and of course those are going to be connected to all access switches redundantly, in a redundant way. So access switches will be connected to both distribution switches. Then what you do, you go on the ports, on the access switches on these ports where you should have only hosts connected. So printers, basically endpoints, printers, IP phones, cameras, whatever. You go on those ports, and everywhere on the access switches facing the endpoints, you configure the feature of BPDU guard, because you don't want somebody to connect instead of an endpoint to connect a switch in the network. You go on there and configure BPDU guard. So let's see that. In my case, I'm going to go ahead and kind of give a BPDU guard between switch 1 and switch 2 to show the capability, because I only have 2 devices running BPDU in the network, switch 1 and switch 2. So what we're going to see is that as soon as I'm enable, let's see show spanning. Well, let's see which one is the root guard, because it's going to depend on that. Show spanning tree, VLAN 1. So another root, which means I am receiving show spanning tree interface FA1020 detail. Okay, so let's go on port 20. Let's consider that, for example, on port 1020, this is a port facing users, and I want to enable this feature to make sure that nobody is able to connect a switch on that port. If it is going to connect, I'm going to put the port instantly into your disabled state. So spanning tree, port fast, spanning tree BPDU guard. Not that. That's a global command. I'm going to enable it at the port level. There we go. So instantly the port went to a disabled state as expected, because the BPDU was received from the other side, because there's a switch connected on the other side. So I just did a simulation behaving like on port 20 I should have a host connected, and somebody plugs in a switch which sends BPDUs, which there we go, the port gets instantly into a disabled state. So do show interface status, error disable. So port 20 is disabled because BPDU guard. If you say do show IP interface brief, include 1020, then here we go, it is in the logical shutdown state. Likewise, you can enable the error disable recovery feature. Disable recovery cause BPDU guard, because by default this is disabled. And you say error disable recovery interval each whatever, like 30 seconds. I think I have configured this from the other topic. So if you say do show error disable recovery, then you should see that for BPDU guard that is enabled, it's also for security. It's enabled for BPDU guard, and it's going to recover the port in the following 11 seconds, because it is going to recover the port each 30 seconds, but I have up to 11 more seconds to wait. There we go. It's activating the port, but it's going to instantly put it down back again because I have a switch on the other side. So let's disable the feature FA1020, no spanning tree BPDU guard. I should be able to say show spanning tree interface FA1020 to verify the feature, but I think because of the fact that the port is being error disabled, I may not see that. Show spanning tree interface FA1020 detail. I don't see this because the port is in the error disabled state, it's shut it down. Let's manually shut it down, and maybe I'm fast enough to show you the output. Shut down, no shut down, and then instantly put the command. Let's try again. Shut down, no shut down. Yeah, I'm not fast enough. With this command, show spanning tree interface is FA1020 detailed. You're gonna see if the feature is or not enabled. But of course, the interface has to be in the up state. Let's remove the feature no spanning tree BPDU guard enable. And then let's put the port to a functional state. There we go. If it's going to be enabled globally, it's going to get activated only on ports where portfast is active. As I was saying before, portfast has its own scope for routing and switching, let's say for switching not performance, but portfast is going to put the port, as I was saying, instantly into forwarding state, and also has a main role into STP and mainly actually RSTP reconvergence. So in RSTP reconvergence, it has a big role. But from the security point of view, I'm going to need portfast to be enabled to be able to activate other security features. Like if I'm going to activate BPDR globally, it's going to get activated only on ports that are portfast active enabled. If you put it at the interface level, then it's going to of course be enabled in there. But if you put it globally, it doesn't get applied. It's going to get applied only on portfast enabled and active ports. Another problem that I could face, another attack, because of the attacker plugging a rogue switch in the network. As I was saying, it can be that the attacker can become a root bridge for VLAN or for all VLANs if it has the proper, let's say, configuration on the switch. So as I was saying, I don't want that because that could create a bottleneck. All traffic is going to follow up towards the root bridge, because when I have redundancy in the network, some ports will be blocking from the spanning tree point of view, some of them will be forwarding, and I'm going to always send all traffic towards the root bridge. That's why the root bridge should be your distribution switches, but that's not a discussion. So in this case, I'm going to send all traffic to the root bridge, which is the attacker switch, which means the attacker, as I was saying, is going to create maybe a bottleneck, but more importantly, is going to get a copy of the traffic of the users. So I'm going to enable root guard in the network, which means that this feature is going to transition a layer 2 port directly to STP root in consistent state upon receiving a superior BPDU. That's like it's not like a logical shutdown. It's like it's going to keep the port into listening state, which means no traffic is going to be allowed back and forth, but BPDUs are still allowed inbound. This feature can only be enabled at the port level. It doesn't have a global capability, and this makes sense because you have to carefully select on which ports you enable that feature. And it's a per VLAN feature, which means that a port may be in the routing consistent state for VLAN 10, but in forwarding state for VLAN 20, because the violation occurred only in VLAN 10. Like the attacker wanted to become a root bridge only for VLAN 10, not for all VLANs. As opposed to other features we've seen before, like BPDU guard and port security, the port is going to be self-recovered from the routing consistent state as soon as the violation occurs, which means as soon as the switch stops receiving a superior BPDU on that port. So now a superior BPDU, how is it defined? It is a BPDU with a better priority than the one of the currently selected root bridge. Where better priority, so that's how the attacker can become a root bridge if it has a better priority. Now a better priority is actually, from the STP algorithm, a lower bridge priority from the value point of view and lower MAC address value. So like if the bridge priority can be anything from 0 to 61,440, then a priority of 0 is better than a priority of 61,440. So in STP, a lower value number is considered to be a better priority, which gives the switch more chances to become a root bridge. So this is a superior BPDU. So in a switch, if for example, let's look at the diagram in here. Like if for example my root bridge would be distribution 1, which actually one of the distribution switches should be the root bridge. And what happens is that if the root bridge is going to have this root guard feature enabled, is going to have it on these ports which are facing the access switches, because I don't want any of the access switches to become root bridges. So I go in here on all ports facing downstream access switches and enable root guard. If the root bridge priority of distribution 1 is, let's say, 61 or 32,768, which is the default value, and with this feature enable a root guard on that port, if the distribution switch receives an inbound BPD which is superior, which means with the priority of, let's say, 16,384, it means that that switch could become root bridge. So in that use case, distribution 1 switch is going to put that port where the BPD was received, the superior BPDU, in root inconsistent state. So like on the diagram, you're going to configure this feature of the root guard feature. You're going to configure it on the downstream switch, on the distribution switches, on the downstream ports facing your access switches. So you're going to go in the network and configure BPDU guard on the access switches facing the endpoints, and go on the distribution switches and configure root guard on the downstream ports facing the access switches. So in my case, I'm going to go and likewise between switch 1 and switch 2, my root bridge is switch 2, should span into VLAN 1 for all VLANs. Show span into VLAN 1. It says that root bridge is not myself. If you go on switch 2 is the root bridge for all VLANs. It says this bridge is the root. So I'm going to behave like switch 2 is my distribution switch and switch 1 is my access switch. Let's go on switch 2 and configure. This is my distribution switch. On the port facing my access switch, I'm going to configure root guard feature. Spanning tree guard root. And if you say show spanning tree interface, that feature, now this command enables root guard on for VLANs. Show spanning tree interface FA1020 detail. There we go. For port 22 for VLAN 13, I have root guard enabled. For VLAN 23, I have root guard enabled, and so on. So to make the violation happen, I'm going to go on switch 1 and behave like this switch 1 is going to send a superior BPDU. It's going to send for, let's say, VLAN 13 for one of the VLANs, a priority which is better than the current root bridge priority, which the current root bridge priority of switch 2, it is probably the default one or not. It is 16,384 plus the VLAN number. So let's go on switch 1 and put a better priority, which is 8192. Only for VLAN 13. So there you go. Switch 2 has put that port for VLAN 13 only in root inconsistent state. If you say show spanning tree interface FA1020, it is, there we go, forwarding for all VLANs except for VLAN 13. It is in root inconsistent state, which means it is blocking. So the switch is going to instantly unblock the port. So at this point, at this moment, all traffic in VLAN 13 in and out is being dropped by switch 2 on that port. So if I go on switch 1, and remove this. As soon as switch 1 starts sending again, in theory be produced so with a lower priority, with a higher priority than the current root bridge's priority, then switch 2 is going to automatically recover the port for VLAN 13. There we go. It says root guard unblocking or unlocking from routing assistant state. And there we go for port 1 for VLAN 13. Now it's going to transition to the regular STP states, blocking, listening, learning, and it's going to go to forwarding within 30 seconds. It is learning now, and of course it's going to go to forwarding within a couple of seconds.